All right, welcome everybody. This is Fred Schenkelberg, and today we're going to go into another one of the fundamentals of a series. I've been doing a few of these, and I've got a few more planned going forward. But every now and then, I feel like even experienced people need to step back and think through what it is we're doing with our basic tools, the fundamental stuff that we do day in and day out with reliability engineering. And as we prompted before the start, a few people have asked some questions about doing HALT and what do we get from it? How do we address questions from people about going over stress and finding failures? Some of those kinds of things. Chris, thanks for your questions. And we'll have plenty of time to address a good number of other ones that should come up. But we'll go over a few of the fundamentals and make sure we're all on the same page with what we're talking about, and then talk about some of the ways that we can get the most out of the process of getting it started within an organization, but then also getting reasonable and very actionable results as we go through the process. So feel free to chime in on the chat window or Q&A pod. I'll keep track of that as best I can, and then we'll go. And hello, Alejandro, welcome, and Conrad, and Chris, and Jim, Ramat, folks from all over the world are joining today. So really appreciate everybody taking time to join me. So let me start off with a quiz for the people that are regular listeners and participants in these webinars. What would be the first worst, the most worst, or the worstest, I'm not sure what the right English is there, four-letter acronym in reliability engineering? If HALT is the second worst, what's the first? Excellent. Thanks, Jim. That didn't take long. Yeah, I figured a few of you would pick up on that right away. Now, I call it a bad name, and no offense to Dr. Hobbs and others that have coined this term and made it popular, but the highly accelerated life test implies that it's a test, that it's something that we can pass, that it comes with the connotation of a pass-fail kind of criteria, which works contrary to what it actually is. It's a process to uncover or dig out weaknesses in designs. It's to explore where the margins are of applied stresses such that it would cause the system or product or whatever we're working on to not work anymore, and not work in some fashion. And so I tend to think of it as a discovery process, and it avoids the discussion about, well, how do we pass this? Now, there's no doubt that that still comes up, and I'm sure you've heard this before as well. Why are you going to go break this? What are we going to learn from that? And so we'll talk about a number of those things today and explore what many of you already know. Why is it so valuable to actually go break things and find failures? And but I think the name of itself actually works against people understanding what it is. And so I know it's cool to come up with an acronym, and it does do highly accelerating, yet it's not a test. It's more, in my mind anyway, it's a process to discover. And so I'd much rather use that term. We have HALT, and that's what we do. Now, one of the primary reasons for using HALT and discovering failures is I go back and cite Henry Petrosky in his book, Design Paradigms, where one of the premises of a good engineering practice is to design away from failure. And one of the roles that we play as the reliability professionals, and why we often use HALT in particular, is that it helps us to identify what can fail. And so engineering teams love a good problem to solve. Now, sometimes we need to help them understand what the problem is. And so identifying those failures, the potential failures or the failure mechanisms that are in the design, allows us then to go address it. the practice of letting our customers find those failures first has some consequences. And I think we're all working to avoid the customer being our test facility, our discovery process. So, as I said, it's a discovery process. Is we're going to examine, explore, play with, um, um, just try to figure out in a meaningful way, how does this process or product or item or component or whatever it is we're building, uh, how does it fail? And it's from that information then that we can take action to do something about it. And so it really is a process to find out what we don't know. And I'm sure you're all familiar with that 2x2 matrix of knowing what you know, knowing what you don't know, not knowing what you know, and not knowing what you don't know. I think those are the 4 boxes. So we're trying to move into the area of what we know, what we don't know, and be exploratory in that way to see what's inside this new item that we're developing and putting together. Right. So real quick, if I'm sure most of you are working on a product or a system of some sort, do you know how it will fail? Do you have a pretty good idea of what's going to be the next failure? Yeah, the stress strength interference is a good way to go about doing it. Many of you probably have immediately thought of different failure mechanisms and different ways things could. Um, I know on my car, I'm approaching, I think, 45,000 miles on it, and I'm thinking, as you are, Rupesh, it's aging. The tires and the tread on my wheels are probably worth inspecting a little bit more often, as I'm probably going to need to replace the tires fairly soon. Right? High temperature, all kinds of different reasons. Now, are you ever surprised? Are you surprised by how your product fails? Yeah, when the customer doesn't like it. Uh, yeah, and you're exactly right, Conrad, is we don't need, if you've got a long list of the way your product fails and things you're going to be working on to make it better, and this often happens after you launch a product and or you've got a long history with a family of products and you're iterating that, you probably already know how your product's going to fail and what you need to go do about it. So if you've got a solid uh, concept of what's going to fail and there's more on that list than you need to work, than you have resources to solve, um, HALT doesn't really add a whole lot of value in that case. I would not recommend doing it. Now, if you've got a new product, a new design, a new interaction element that has a lot of unknowns or uncertainty around it, well, then HALT is a really good tool. It's that, keep in mind that it's chipping away at what we don't know, or in some cases, what we know we don't know. It allows us to probe into areas that we suspect may have failures lurking in them, failure mechanisms, and it allows us to go after that. And so it's part of that process of sorting out what's going to fail in our product and to minimize or avoid the surprises that we get and that our customers see. Right? So that's what I think is its primary process to it. Now I'm going to take a quick look at the chat because there's a few things going by there. Um, yeah, Ropesh, looking at the margin is the way I would phrase what you're talking about, the factor of safety. Um, so we expect what our customers are going to use. We have some expectations of how our customers are going to use our product and the environment and stresses they apply to it. And then we generally design so that it's going to survive in those environments by making it a bit more robust than just on the edge of it. Because there's variability. There's variability in materials and assembly processes and how customers use products. And then there's accumulated wear and damage that occurs that will weaken the product at various rates, depending on its particular circumstances. So we tend to build in some robustness into a product. And so HALT is one way for us to measure that margin, that margin factor of it. Now, it's not, if you really need to understand what your stress strength curves look like, what the strength of your product is, running one or two products in HALT is a glimpse of that, just a sneak peek at how much margin you have. It doesn't fully characterize it, right? So you do need to think through, for the areas of highest risk and areas of most uncertainty, you may need to do more characterization type work, looking at what is the variability that we're getting in our product for all the various reasons. But HALT can help us narrow that down to the areas that have obviously the weakest areas, the least margin at all. And so one of the things we're looking for here, and I'm going to go over this fairly quickly, is there's a handful of steps to keep in mind as you implement HALT. And so the first step is, well, how can it, what are the stresses? What's the environment that you're putting your product into? Where's it going to be used? Just the other day, I was talking to a director of engineering, and they're working on a novel, brand new product. It hasn't been in the field at all yet, and there's no real competitors for what they're doing. It's one of these classic startups here in Silicon Valley. And I asked him, so who's going to use your product and in what environment? And he says, well, we've kind of thought that it's at a home, maybe a business, and it's portable, so it could go outside, but we're not real sure. And I'm like, okay, well, how often do you think it'll get dropped? Well, we don't really know. How often will it be used? How often will be people interacting with the product? Well, it's so new, we really don't know. We think it'll be a lot at first, and it probably taper off. And there was a lot of hunches and guesses at the start. And so if that's all you got, then it's time to put on that brainstorming process, is to really open up what are all the ways, even the crazy ways, that could cause a failure to your product. Now, the easy one is a lightning strike. You get a direct lightning strike to your product, and for most of us, that would pretty much destroy it. Now, we're not going to design a portable electronic system to survive a direct lightning strike. Yet, what about power surge at plug-in when you power it up? What kind of if somebody inadvertently plugs it into a 220 volt versus 100 volt or 120 volt, what will happen? What if the power is high that day? It has a power spike that occurs, or a power brownout or a dip. What if it goes 20% high or 20% low? And it's the what if scenario. List as many as you possibly can. And one really, really good technique is to use the work you've already done. If you've done an FMEA, if you've done a risk assessment, and my cat likes chiming into this, I'm not sure if you can hear him in the background, is use that as a starting point. Here's all the ways that you've already thought through how it can fail. Now, what are the associated stresses that would be involved with those failures? And then another good technique in brainstorming is to use anchoring and help people see the problem from a number of different perspectives. And so if I say, like on this next screen, I think I have the cell phone. Let's say you have a cell phone. Most of us do. What stresses apply to a cell phone? How is it likely to fail? And I'll throw out temperature as a one. You know, put it in the dashboard of your car for too long. I know mine, even on my deck, when it sits in full sun, it gets really warm. Drops, yeah, ball drop, dashboard test, yep, got a mark. So if you think through how it's used, right, you start thinking of the stresses that it's going to see. What's the day in the life of a cell phone, right? And Tamer, you brought up one that's not related to what I was the day in the use, but shipping, the transportation process, the installation process. So what stresses apply in shipping that don't apply in normal use? Sometimes it's very, very different, and sometimes they're similar. And yeah, water ingress. Now, that's been a known problem for years and years and years, and now phones are coming out with more water resistance or waterproofing as they uh, do that. Uh, Nobody mentioned my daughter. I think she's gone through like 5 or 6 phones. Her last one, she had it put together with duct tape and shipping tape so that she could use the screen still, but it was completely shattered. It still worked, but it was very hard to read the screen, so she was able to do stuff. Yeah, software and so on. So as you think through what are the stresses that could be applied, and we've got everything here from UV to shipping, humidity, a lot of the common ones. How about insects and biological threats? How about cosmetics and lotions and things that are found on people's hands? Sometimes I don't like thinking about that too much. So I apologize if it's lunchtime for some of you, but that's an anchor, right? It shifts the way you think about what are the possible ways that a stress could be applied to a cell phone that the cell phone would see. Yeah. Yeah, I've heard that banana boat actually is a really aggressive chemical, basically, against various products and handheld products. There's some perfumes too that are pretty damaging to finishes. Yeah. But then you're right, Tamer, there's also the reverse. How can your finish on your product affect the person themselves and cause a failure to occur because they get a rash, for example? And so that's the idea, is what are all these stresses? Now, are we going to test to failure and explore how it's going to fail with every one of these stresses? Right? Probably not. We, as much as I'd love to, is to test everything to failure. Now, some of these things that we've listed out are we know are going to cause a failure. We know that dropping a smartphone is going to cause failure or accumulate damage. And if we're working on a design to make it more robust to drop damage, it may make sense then to drop to failure or do a single drop to failure, keep going higher and higher, and maybe start shooting it at the floor, which is the velocity that will cause damage. And compare that to what's the typical acceleration and velocity that we see on impact in normal use, and how much margin do we have? But if it's a known issue and it's not causing us significant problems with our particular product's application, we may skip that particular stress and move on ones that are more unknown, areas that we're exploring more. So like UV and the chemical ones, if we're putting a new finish on the surface of our handheld device, we may want to explore to failure all the different ways that it can fail from a chemical attack or from UV degradation and run it to failure and see how solid we are. So part of this process is narrowing down the list is, well, what's the highest risk? What are the areas that we already know have minimal margin or safety factor, or areas that we just don't know? We don't really know how this new finish will survive a freeze-thaw cycle, for example. Will it buckle and delaminate from the surface if it does that? So sometimes it's based on where we know we have minimal margin. We want to verify that or determine where that margin is. But sometimes we're really just exploring. And so those stresses that we pick are to help us answer questions and to some extent probe into what we don't know. And so I keep coming back to that. It really is an exploration process that we're after. All right, so then we narrow this list down, and then the creative part really gets to is, well, how are we going to do this, right? And so Drop seemed to be a good one, but there's chemical and all these other things we can do to a cell phone. But let's narrow it down to the ones that are relevant for the areas of highest risk and or areas of most unknowns. And so it's a way to narrow it down. Now, let's say we pick 5 different stresses: UV degradation, moisture exposure or water exposure, um, drops, and high temperature and thermal cycling, right? And some of those we know are going to cause failures in one way or the other. If we drop it and just keep dropping it, we are going to cause a failure for a cell phone. So the basic process that I advocate for exploring these things, right? I'm seeing all kinds of cool stuff now coming across. Yeah, give my kids the electronics. That's the and now you're getting tons of other areas here. Um, but if we're going into the lab to explore what causes a failure, and we end up with, say, 5 different stresses that we're interested in, and notice that in the last 2 bits of this, we did not talk about a HALT chamber, right? A HALT chamber is great. It has temperature controls, vibration controls. You can often bring in other stresses like power and voltage margining and other things like that, and loading systems up with high data streams or whatever. That, in my mind, that's not where you start. Just because you have a HALT chamber doesn't mean everything needs those particular stresses. Many HALT experiences are done on a benchtop, are done in the factory floor, are done out on the street, are not done in a HALT chamber. They are convenient and they work great for electronics because a good number of failure mechanisms for electronics are accelerated by temperature, thermal cycling, and vibration. But if your product is not dominated by those 3 stresses, then a HALT chamber is probably not your first choice. So if, like for the cell phone, we're talking about software glitches, UV exposure, and drops. And it doesn't make all that much sense to go to a HALT chamber to do that. So back to the basic approach is use one stress at first and take the stress that is least likely to kill your samples. The samples we get are often both scarce and expensive. And so let's not break it on our first 10 minutes of exploration, but let's explore how far can we go to where we expect it to still work. Maybe go to what we expect our customers to see with the product. So it might be, say, in temperature, is go to 40 degrees C. And will it power on? Will it start? Will it make a call? And do the evaluation of that. And so, is it still work? And then let's back off. Let's go to low temperature. And let's do a couple thermal cycles in that envelope of where we know it's working or should work. And then go to the next stress. And what's the range of values we expect it to be used in? So explore each of these stresses into the areas that we expect it to work. A technique I use oftentimes and highly recommend you do is bring a design engineer with you to the lab, right? And as the stresses go up, you'll see them get more and more nervous, especially when you start going well beyond where the product is expected to be used. And use that as a gauge to where they best know their design. They should know where it is likely to fail, where those margins are, where the unknowns start to become. So at the start is start slowly and use individual stresses and map out the areas where it should work. And then circle back and map out where you get your first failures, right? Just step stress till you get a failure. The screen goes blank. It won't make a call. It won't power up. It won't take a charge. whatever it is that's your criteria that you're measuring, is start measuring each of these stresses individually to find out where it starts to create a problem. And then start the failure analysis part immediately. Capture all the details, capture all the information, capture the scenario, the situation, and the symptoms, right? And then a good technique is to back off, go back to nominal conditions. And if the product recovers, well, it's an operating limit to your product. So instead of 40 degrees C, we see a first failure at 80 degrees C, and it recovers when we go back. It might be an intermittent problem. It might be a timing issue. It might be some other phenomena that manifests itself at 80 degrees C, but doesn't cause permanent damage. It doesn't break a solder joint, for example, or destroy an active circuit such that it doesn't function anymore. And so what we're looking for is those operating limits, and we can identify them by backing off the stress, and it comes back to life. It's still functional. But as we find those things, can we isolate those? Can we remove that failure from occurring? Can we repair it, replace it? In one product, we had a spinning hard drive, and we knew at very low vibration we were going to expect failures, and it did. It failed with very low vibration. So we isolated, suspended the hard drive above the table so that it wouldn't see the vibration experience, and then the rest of the system saw more vibration and helped us find even more failures that we could take care of and add more information out of the tests that we're doing. And so as you explore the individual stresses, now start combining them. Now, customers naturally use all stresses simultaneously. And so part of the idea behind HALT is that we combine stresses to find those interactive elements that cause failures to occur. And a study by Mike Silverman, when he was running the HALT labs here in Santa Clara, found that about 20% of the unique failures that were identified in the HALT tests he did with many, many clients was only found in the combined stresses. And so that's, I think, where the real value of HALT comes, is that this notion of combined stresses allows us then to explore things and find things that we wouldn't otherwise find with the traditional way we explore our products. And so let's say we're evaluating our cell phone and the screen goes dark at minus 30 degrees Celsius. So what should we do? What's the immediate steps and then long-term steps we should do when a screen goes dark at minus 30? Thanks, Andrew. Yeah, back off. See if it's an operating limit. Yep. Now, Rupesh, why would I check the user scenario? I'm in the HALT chamber, or in the HALT sequence of testing. I'm step stressing. Expand on that a little bit. What's your thinking of going after the user scenario? Oh, if the user wants it at 33 degrees. So is this something I need to take action on? Now, I think one of the key points here is that even if we only specify the phone to work at, say, 0 degrees C and above, I appreciate it, Tim. Celebrate the failure. If we got something, we can work on it now. Is there enough margin? I think that's what you're getting at. If we're below, if we're within the realm of where we expect customers to deal with, it gets a higher priority for failure analysis and further work. If this is really 30 degrees of margin and it's not a permanent damage, then it's less of a priority. But in either case, celebrate the failure, document what you know, do the failure analysis, and understand why it occurred. Let's see if anybody mentioned it. Yeah, where's the problem? Alejandro is right. Sort out where it is. Is it a soft failure, a hard failure? all those kinds of things. And then Mark, exactly right. Is this the technical limit? On some screens, I was working with some LED screens a few years ago, and at about minus 30, they would just go dark. And it had to do with the technology that was built into the screen. It wasn't LED, it was a liquid crystal, I think, or some older technology. And since it wasn't in the use profile to really get to those temperatures, it really wasn't a relevant failure that we needed. It verified that the technology failed when we expected it to fail. And unless we had an application that would go colder, we would have to go to a new technology to solve that problem, to get it to work at a lower temperature. Also, being the first failure was at the limit of that material set was that we had the right design, that we were on the right track. Now, this is assuming that we understand how our customers are going to use the product, but it was very informative in all of those realms. And so part of it is understand. I think you're onto something there, Rupesh, where it's, well, what's this kind of margin are we getting? Understanding the failures and celebrating that and going after what exactly is going wrong with it, gathering all that information. And then a number of people chimed in is, we'll step back and see if it's an operational failure or a hard failure. And do we recover or not? Right? So all excellent, you got it. But it's a thinking game, basically. As you go through the process, as you see failures, it's not avoid that area anymore. This is where we go learn stuff. This is where we pick up information. So that's where the failure analysis really starts, is that just as we get a failure, as we get an anomaly or something doesn't look quite right, it's worth being well prepared going into the lab to make sure that you are sensitive to what you should be seeing versus what you are seeing. Years ago, I was working on a handheld microphone system for an entertainment system, and the handle had a bunch of lights that would flash with the music and with different actions and as a feedback mechanism to the person using the device. And we're applying some vibration, and all of a sudden the lights all went purple, which wasn't one of the colors it was supposed to do. And it would just stay purple, and something broke, something failed. Turned out, as we took it apart and evaluated it some more, is the crystal. The actual crystal broke. That was driving the timing for the circuits. And when that broke, it just happened that the symptom was that it would turn all the lights purple for some reason. It was very strange. But we found that the vibration flexed the circuit board at the highest deflection, right under where the crystal was mounted. And so moving the crystal and dampening the board and mounting it a little bit differently solved that problem, gave us way more margin for vibration. And this was a product that was intended to be used as a game, and one of the actions in the game was clapping your hands. The device had a way of measuring if you were on beat with your clap or not. And so that slapping shock and vibration mode was something we were rather concerned about with this circuit board flopping around inside of it. But then go into the normal root cause processes. Start asking lots of questions. Why did that happen? What caused that? What caused that? Why? 8D process is a more formal one, where it's gather the information, do the detailed analysis down to chemical, physical levels, get a good understanding of it. Can you repeat the failure? I also like the 8D process because the last step is to celebrate that you completed the process. So I've seen companies do a 7D process where they skip the celebration part. But I think that's missing a key point to putting together a detailed failure analysis. Is the understanding is something worth celebrating. So those are the basic steps, right? And we're driving towards understanding how our product fails. And we're celebrating those failures. Now, part of this, do we know we have the root cause, is that we can turn it on and off. We can characterize it and we understand how it works and doesn't work. And at that point, then we may have to make a decision. Are we going to fix this or not? Now, these failures are not sorted in any way at this point. As we come out of the HALT experience and we've tested a variety of different stresses and maybe found 10 to 20 different failures, some of which we knew about and some of which we don't, is then which ones are the technological limits of our materials? Which ones create safety hazards? That same handheld microphone had a failure mechanism we discovered that dead shorted the battery pack and melted the polymers that were inside of it, created a burning smell. We don't think there was enough power in the two AA batteries to cause a problem, but it sure created an unpleasant experience for the user, and we didn't want to risk that it would cause a fire. So that became a very high priority. Now, other things, maybe with so much margin that the chance of it occurring is very low, and so we moved that to a lower priority. Things that had very little margin ended up being a higher priority for the team to address, to build more robustness into the system. Yeah, and I'm looking at your comment, Tim, is one of the, Rufus, and there's a couple other comments, and one of them earlier was this notion that it failed at high stress. So if we're rating this phone to only work to 40 degrees C, and we see a failure at 100 C, you're going to get some shrugs and why, what do I need to do about that? Well, that's where that failure analysis comes into play. Is this a failure that is an accumulated damage and will occur anyway over time because it's going to accumulate damage at lower temperatures, for example, or different vibrations or lower shock rates, for example? If it's an accumulated damage, then we may need to answer the question, well, how long before it will actually fail? Which was another one of the previous questions was, can we predict life based on a HALT test? In my opinion, no. It gives us a glimpse into what the failure mechanisms are. And then depending on how well we understand those failure mechanisms, can we then predict life? We may need to do accelerated life testing, which is a way to characterize time to failure. Yet HALT in and of itself gives us ideas of the focus is what fails. Drive it to failure. And then we can make decisions about how to make the product more robust. Dr. Hobbs often said it's a build, test, fix algorithm. Find what fails, improve your product so that doesn't fail again, and go look for the next one. And keep doing that to make your product as robust as possible. And so if we get a failure in the lab, oftentimes one of the early steps is, can we replicate it? And that's a step towards understanding it. What were the conditions that caused that timing error to occur or that software glitch to occur? And it helps us in diagnosing what's happening that causes it, the chain of events that lead to the failure. Understanding that chain of events helps us to figure out where to interrupt that process and to mitigate or eliminate that failure from the design. Yet, if we see it once and we don't see it again, it's also worth asking the question, was it an intermittent problem? And if it's intermittent, how many units would it affect? And so some are rather difficult to find. And it's a judgment call as to how long do you pursue tracking down intermittent problems. And depending on the nature of the problem that you saw, if it's more urgent or safety related, then yeah, you'll spend more time tracking down an intermittent problem. If it's an anomaly and it self-corrects very fast and it's only 1 in 100,000 hours that it occurs, well, we'll probably not spend too much time on it. So it really is a thinking game as you start learning things is, well, what do you need to know in order to make good decisions about these failures that you're seeing? Now, most of the time, it's getting to that root cause. is truly characterizing what happened. That allows your engineering team to make good decisions about how to whether or not to address it, and whether or not their design has got enough margin. Is it robust enough for its intended application? What we add is that layer of just because it failed at high stress, it just did it faster. That's that accelerated part. If we go back to normal use, that failure will still occur because it's accumulating damage, for example, or it's wearing, or it's degrading. And if you want to, we can predict when that will occur. But given all of the ways your product can fail, these are the things we saw as weaknesses from this test. And those are our best clue of where we can best, most effectively, most cost effectively make the product more robust for all failures. And so the because it failed at a high stress does not mean that that's the only place it's going to fail. It's a couple of units. We're not looking at all the variability of our use cases. We're not looking at all the variability of the manufacturing and the materials. And these units chose to fail at these points. Understanding the failure mechanism, understanding whether it's a technological limit or not and how much margin you have versus your use conditions will help you prioritize which ones need to be addressed. And so a good part of the preparation for a HALT test is really helping your team understand that we're not so interested at where it fails in the stress application, but that it failed, that the failure mechanism actually occurred. Now we can go learn something about it. Now we can go improve the design. So shift that focus to, are we addressing the failure mechanisms, and do we know all of the failure mechanisms that are relevant for our product? So the basic concept is in a large part done in the preparation. What's the scope? What are we studying? What's the element of this? And then more importantly is, how are we going to measure it? How are we going to know if a problem is existing or not within the product? Now, some products are obvious. It's the whole interface tells you the whole story. It's like the cell phone and its screen. If there's no screen or there's no signal, it's not working. Yet if we're more interested in how clear or stable a signal is, or how powerful an output antenna is, we're going to need a way to measure that, some way to detect when there's an issue or a problem. And so it's pulling together those different pieces and then answering the question of, well, how are we going to apply these stresses, and how are we going to apply these stresses in combinations? A common question I've gotten over the years is, how do I do temperature, vibration, and humidity? And the chamber makers tend to not like humidity because it wears out the chambers pretty quick. It causes problems within the chambers, especially the vibrating elements of it. And so you don't find chambers like that very often, and when they do, they're rather expensive because they don't last very long. So you may have to think through how you're going to apply the different stresses, and maybe using different chunks of equipment and different parts of the process as you apply these and make the measurements to check performance. And then it's really, what are the known failure mechanisms? What do we expect to fail? Now, I think this is an important point, is if you know what to expect, you're much more likely to detect the things that are unexpected. Is prime yourself to know what you're looking for and be willing to be surprised. Yeah, and Tim, and yeah, you're right. There's another problem here, especially when you're planning it, and especially when you say, I'm going to take this 2 prototypes or 4 prototypes, and I'm going to break them. I am deliberately going to break them. That usually causes some tension with the rest of your team, who desperately needs working prototypes to do their job. So the real crux to this is, what are we going to learn from this excursion into finding failures that we're not going to get otherwise, that we'll get later in the program? And oftentimes the argument is that we're going to find failure mechanisms sooner than later. A lot of our environmental testing and later testing and verification that we're going to do is going to find problems. And if we have more time earlier in the program, we can solve those. So what we're getting with HALT is the benefit of time. Now, typically it takes a day or two to gather all the equipment and prepare for the doing the HALT, doing the application of stresses, maybe more if you have to develop jigs or fixtures or so on. And then it usually takes 2 to 4 days of in the lab pushing things to failure and documenting and gathering the information. Depending on what you find, it may take some more time to do the failure analysis. So overall, on the order of 2 weeks for a couple of engineers and a couple of prototypes that are going to get damaged. In return, you learn things that you otherwise would not know. You learn things sooner than later in most cases, and you determine the margins or estimate the margins on a number of your different important stresses for your product. And so the feedback in a number of different ways help you understand, is your product robust or not? And if it's not robust, how so? And so let's go to this question on the screen, is if you're going to do drop testing, how high do you go? How much stress should you apply? I should have put the picture of the egg and the mallet here. Is how big of a mallet should you use? Yeah, so yeah, I'm going to go to the third answer I'm seeing from Brian is go until it breaks. Right? Now, the hard part with drop is that it oftentimes is accumulated damage. On a handheld device I was working with one time, we went to 116 drops from, I think it was 6 feet before it stopped functioning. Now, there was some marring and scratching and some deformation on the outside of the thing, but it still worked. We went 116 6-foot drops onto concrete before we got a failure. And what we found was drop was still the #1 stress that was going to cause our product to fail. And so into production, we used that HALT test as a basis for monitoring the robustness of the assembly. And so we said drop to failure is every day we picked 1 unit off of this production facility and dropped it to failure. And we put a Q-sum control chart on the results of that on a day-to-day basis. And the first signal we got was, instead of between it was 90 and 120 drops these units would typically fail, we got one that failed after 30 drops. And so we stopped the presses, we did a bunch of root cause and analysis and investigation, and we discovered that one of the critical glue processes that held the enclosure together was desperately trying to keep up with production, so they added a manual station. And the people that did the manual gluing versus the automated glue machine that was applicator that was used was nowhere near as consistent, which wasn't surprising. And the units, we happened to catch one of the units that was done manually and found it nearly immediately and avoided a huge problem going to the field where very subtle drops relative to how robust the design was would cause it to shatter and fail. But test to failure. Are you going to a technological limit, or are we going to a variation in the process that we're discovering? Or, and in comparison to our use conditions, do we maintain the margin that's in the design? And is it still there? But as I'm dropping something, I would go until it fails. The standards often say stuff, especially for drops, IEC and ASTM say 10 drops per face or 3 drops per face on a certain material and stuff. And they make it a very standardized process. But let's say I drop a cell phone 30 times and it passes the IEC standard. What have I really learned? What, what does that mean other than I can put it on the data sheet? Not a whole lot. It doesn't tell us what our margin is. It doesn't compare us to the use conditions and so on. So one other quick story, and some of you may have heard it, is I was working with a team that made baggage handling barcode readers. So the guys on the tarmac were loading and unloading bags and cargo on a plane would read the barcode tags as they got put on and off the plane. And those things were portable, and they took a lot of abuse. They got thrown around and dropped and kicked and run over and all kinds of things. And so what this organization did is they started with the IEC standard, and they dropped it, I think, 20 times from a certain distance. And they ended up with lots of field problems due to shock damage to their product. So they increased the test to check, to build in more margin. They had to pass now, instead of 6 feet, 12 feet, for example. And their warranty costs went down due to damage due to drop. I think the last I knew of them, they had cut a hole in the roof of their lab and they were dropping it from 18 feet, and it was like 50 or 60 times. The hardest part was, instead of making a tech climb up and down the ladder to drop this thing, they set up a mechanism to hoist it up there and release it in a random way to speed up the testing process. But their design continued to improve, and they needed more and more stress to prove that to provide feedback as to when it would fail. And so with any of these stresses, if it's what's causing customers to report failures for you in the field, there's no standard or internal documentation that's going to say it should pass when your customers are saying it's not. So increase the stresses. Keep going until you see where your margins really are. Now, in this case of the handheld baggage readers, they made it an internal requirement. You need to pass 50 drops at 18 feet. I don't know of any standard that calls that out, but it had a direct correlation to their field performance due to the stresses applied by their customers dropping it, or the baggage handlers dropping it. All right. So the basic idea here is we're finding limits. We apply the stresses, we find something that doesn't look right, doesn't work, it's failed, and we back off. If it comes back to life, we're going to define that as a operating limit. If it doesn't come back to life, if we actually fractured something, if something broke, if something won't power on anymore, then it's a hard failure or a destruct limit. And so that process of testing one stress at a time and stepping out slowly is a way to find those operating limits before we jump and find a destruct limit. The idea is to gain as much information and find as many different failures as you can from the few samples that you have available. So I'll leave this one as a kind of an obvious one. If we melt some part of our system, is that going too far? Well, no. We found a technological limit, and then it's a judgment, is that a limit that we need to change by changing the basic technology. So ideally, we test a product and it goes to the limits of our capabilities of the material sets we have available. And we know that there's no internal design or interaction or manufacturing flaws that will cause it to fail before the capability of the material sets that we have available. And so the idea is to test until you hit these technological limits. And then it's, do we need to go beyond that? So for years, the cell phones were not really all that water resistant. Now the technology has changed, and we're doing water testing to much higher stresses than we ever did before. So as the technology changes, our limits change. So as we find stuff and understand it, we start prioritizing. in sorting out which ones that we need to deal with. Once at the technological limit, it's in relation to how our customer is using the product. It always is. So that discussion, I think, Rupesh, you mentioned it a couple of times. It's keep in mind how our customers are using the product. I would add is that our customers are constantly changing the way they use our products. And so it's not an ending process. We got to keep working on it, keep moving through this. And so coming up on the end of the hour here, so I'm going to just ask, how are the HALTs working for you? What other questions do you have that we may have not addressed here in the bulk of the presentation? And I'm going to mention bulk of just a couple of them as you get a chance to ask a couple of questions. Is what could you do wrong? One of them is only do testing that's in a HALT chamber. Now, in some products, some product lines, that's the right set of stresses to use. Yet, if you're missing other stresses that are important to your customers, in my opinion, you're not doing HALT. HALT is not a chamber. A HALT chamber is convenient for some stresses, not the other way around. Don't limit your testing to just what you can do in your chamber. The other one is just run a standard profile. I ran into one lab that they were so busy with so many prototypes that they only ran a 2-hour profile on every product. And very, very, very few things failed. Well, that's not HALT. That's an environmental test and probably not all that useful at all. And finally, this one should be easy to understand. If you don't follow up, if you don't have those discussions with your team about what actions to take to make your product more robust, there's very little value in HALT. It's not a checkoff box. It's not just go do HALT, make it fail. It's the value in it is in doing something with it, is improving the product. Yeah. So Simon, when you end a HALT, it's not a pass-fail. It's here's a list of things that we need to go investigate and work on and make our product more robust. Now, some of those failure mechanisms may spark a physics of failure type analysis or an accelerated life test. That's very true. Yeah. William, you're right. One of the ways to look at a product, especially when its look and feel is important, is those tolerances. So you might have to be a little creative of how you, in an ongoing test, is how you measure those things. But other things like sound, how does the product sound when it starts up? Or how does it sound when it's operating? I'm thinking of inkjet printers. If they used to sound absolutely horrendous and screech and grind and sound like they were going to chew up like all the paper and ink. As the designs got better, they got quieter and quieter and also stopped walking off of tables. But measuring sound power isn't the whole equation. It's the quality of the sound or the nature of the sound. And so how would you measure that and follow up on it? Yeah, there's lots of ways HALT can go bad, but just real quick in summary is and I'll stay on the line for more discussion and questions, but respecting those that only banked in an hour, is do the planning up front. What stresses are you going to apply, and how are you going to apply those, and how are you going to measure it? Go find the operating and direct limits. For me, a successful HALT is where you find 25 or more failures and have information on those failures. And then the value comes out of resolving those problems, making your product more robust. So a bit more information. And one last thing, I'm going to do a commercial plug here for a book I'm working on with Carl Carlson. And I don't have the link for it here. So let me go to the conclusions page. And in the links in the lower right-hand corner, there's the Reliability Engineering Management book. Carl and I are working on a book for Reliability Engineering Management, and you're invited to help us review it. We've published 2 chapters so far, so far. With sign up to the Sendo site, you have access to those chapters, and we've been getting some just amazing feedback and comments and recommendations that's only going to make this book a whole lot more valuable for you. So we're inviting you to take a look at it and give us your feedback. Give us your ideas and insights and comments about what's going wrong with this. And Rupesh, just saw your question pop up there. A sample size. Um, in practical sense, is whatever you can get. It's because we are going to destroy it, and it really depends on what kind of product you're building and how expensive the prototypes are. But typically, we go into the lab with a minimum of 2 samples, 2 units, and we focus on one until it's just not usable anymore. And then we may swap into the second one. If we don't have to destroy the second one, that's great. We can return it back to the system. Others advocate that we use 4 samples. Now, 4 still doesn't give us a statistical sampling, but it gives us more information about the variability in the design and its assembly process. So we're not really trying to do a statistical based test. So the sample size is typically 2 or 4 units. Yes, and definitely repair and continue HALT. Is you find a failure, isolate it, put a new motor in, change the screen, duct tape it. There's a lot of duct taping and baling wire just to keep it running, and go find the other failures. Those are all good stuff. So Tamer, a HALT to me is a failure as a process when you get no failures. So running a fixed profile or running for a limited time, not running until you get to technological limits, is you're not getting the benefit of the HALT. Yeah, sometimes we're beyond this capability of the equipment we have and our creativity of causing failures. But it's harder to interpret that than when we actually get something that fails. Yeah, Conrad, I'm seeing your supplier HALTs. Yeah, some are, and I've seen this in a great number of different realms where HALT is a great buzzword. People say that we're going to go do HALT. It's sort of like process control and control charts. Yes, we do control charts, but then it's obvious they don't actually use it. It's just wallpaper. It's the same with HALT or even FMEA. All of the tools we use can be done really well or not. And the difference between really good programs and organizations that really care about reliability is they take the time to do it well. And so hence a lot of the focus of these fundamentals webinars is understanding the basics, but also how do you make it work? How do you make it derive the value or create the value that they should? Huh, interesting, Conrad, doing them together. I wonder if that's after the variability, because just depending on the stresses you're applying, that could be technically difficult to do them simultaneously. Or if you do one or the other and do comparisons, I can see that. It's pretty common. Okay, so I'm going to go ahead and end the